We are back on our last section of Thermo. Some of the things we'll talk about today actually are included in section 17.1, which you've already read. And so we're going to look at chemical reactions. Okay, so we know in a chemical reaction we have bonds, right? So what we have down here is methane. All right, we've got a bond here, here, and here, and here. Methane react with oxygen. This is just our combustion. We're burning, so we have double bond and double bond. So what happens is in any chemical reaction we have energy involved, right? So we know a reaction can be endothermic or exothermic. Okay. How we would look at that is anytime we break a bond. So we can think about this as every one of these four bonds in methane and all two of these bonds or both of these bonds in oxygen, we break apart. It takes some amount of energy to do that, right? Energy is always required to break a bond. And we can think about it as now having all these individual atoms. Okay? In reality, we don't see all those actual atoms. We have like activated complex and stuff. But as far as the energy involved, we can think about individual atoms and then all the new bonds formed to get our products, which are carbon dioxide and water. Okay? Anytime a bond is formed, it is exothermic. Energy is released. Okay? So it's really just the difference of how much energy did we have to put in, how much energy do we get out when the bonds form. In this scenario here, we know from experience that combustion is exothermic. We're going to get off heat and light or fire when we get those products. So we must have got out more energy than we put in. Okay? We're not going to do calculations of the specific energies of breaking bonds and forming bond. That's for next level. But that's the concept here. Remember, to break a bond, it always takes energy. When this bond is formed, some energy is released. The difference between that energy put in and energy got out is our heat of reaction. Okay. So we were just saying, we put in some energy, we get out some energy, right? If the energy we put in to break all the bonds is less than the energy released, okay, it's exothermic, as our previous example. And then, hopefully, obviously, if the energy required to break all the bonds is greater than the energy released, it's endothermic. So we put in more than we got out. That means net, it had to absorb energy, or it's endothermic. Okay. So the difference between the energy added and energy released is the heat of reaction, or enthalpy of reaction, and this is our delta H for our reaction. Sometimes we put the Rxn down there just for delta H of reaction. For us, we usually just leave that off and just write delta H. Okay. Another way to say this is if the potential energy of the reactants is greater than the potential energy of the products, it's exothermic, right? Because this is storing essentially a certain amount of energy. If this is storing less, that means we had to have given off somewhere. And of course, just the opposite, if the products are greater than reactants, it's endothermic. This is going to lead us to potential energy diagrams that we had talked a little bit about in the equilibrium unit, or the previous unit. We're going to go into here and look at it more in terms of the energy of those. So now we're going to look at the reaction coordinate diagram, or also called the potential energy diagram. You will see both of those terms used in our questions and on our tests, so please recognize those as the same thing. We usually introduce them here for the first time, but because we did the other unit first, we've already introduced them, but we're going to go over them again here and look at this in terms of more of the energies involved, right? So we find the energy on the y-axis. Many times this is labeled potential energy. Again, one of the reasons why it's called potential energy diagram. On the x-axis, we have reaction, right? And the x-axis has little meaning. It's not ever to a scale. This can often be to a scale because you'll have usually kilojoules per mole or something, usually kilojoules per mole over here on the y-axis. This just means sort of as we proceed, right? So in this other term, sometimes called a reaction progress diagram, because it's like the energy as we proceed, right? The reactants start at some amount of energy, which we would read from the y-axis if there was a scale on it. We know we have to get this activation energy. We've got to put in some energy to get the reaction started, and when we're done, our products have a certain amount of energy. Okay. So does this diagram represent an exothermic or endothermic reaction? Again, we've already talked about these. Hopefully we recognize that, but we can see these are higher, the reactants are higher than the products, so this is an exothermic reaction. We see here from the reactants to the products is our delta H, our heat of reaction. So the difference of the energy of the reactants and products is where we get that delta H. If we had numbers, we could just subtract those two. So if this were like 100 and this were like 250, our delta H of our reaction would be negative 150. All right, it's always final minus initial. So 100 minus 250, as we would expect, it's negative because it's exothermic. Okay. Well, if we look at the reverse reaction, is that exo or endo? All right, so we don't really need to draw it. We can just start here. And now products, and as we talked about before, with reversible reactions, the terms products and reactants have little meaning other than what is on the right side of the reaction and what is on the left side. So when we look in reverse, we're starting here at products, going backwards. So the reverse reaction has to be endothermic. Right? An important idea that any reaction, if one direction is exothermic, the other direction has to be endothermic. But also note that our heat of reaction is going to be the same numeric value, but the reverse reaction, so our delta H of the reverse, if we use the same numbers we had before at 100 and 250, so the heat rate delta H of our reverse reaction is going to be positive 150. So again, exact same value, just different sign because the energy difference has to be exactly the same. Okay, just to look at some of the definitions, make sure we're all on the same page. We have our activation energy. That is the energy required to start a chemical reaction. Okay, so we actually did look at this a bit closer in our previous unit. Remember, there's always some amount of energy that has to go in. In our collision model, we said that there has to be enough energy. That enough energy is the activation energy. In the baseball analogy, we had to hit the ball hard enough to get over the fence. That is our activation energy. The activated complex is this blob of stuff that exists. We'll look at a picture on the next slide, I believe, but it's what exists at the top of that hill. So if we've got our diagram here, right, we're breaking these bonds apart. We're starting to form the new bonds. Right at the top, we have the activated complex. I won't write it out anymore. You can't read that. Transition state is that time at which this activated complex exists. We're transitioning from reactants to products. So the activated complex is the thing, whereas a transition state is sort of this part of the graph. Right? It's in a transition state when we have the activated complex. Okay. All right, so this diagram isn't coming out very clearly, but we have our collision here between these two molecules. We have this activated complex where the bond here is starting to break. The bond here is starting to form. And so it's really one sort of big blob of atoms. And so that's our activated complex, and we get our products. Okay. And we can notice from here our reactants start at this energy, our products are higher, so this is an endothermic reaction, and our heat of reaction again would be this. If we had values to read off the graph, we could do that, which we will in a moment. And again, the activated complex, or the activation energy, is always to the highest peak, and it is always higher than either the products or reactants. So if we look at a graph, we have several letters on this graph. We have a couple more things to add, but we can get the energies involved in all of these, right? So what we have is, we're just assuming this line is already labeled 0, right? So whatever values this is, right, we have some numeric value. Actually, let's just put in some. Let's try to roughly evenly space these. So we'll call this 100, 200, 300, 400, 500, 600. Okay, and this would be in kilojoules. All right, so going from 0 to there, that just tells us that, well, at 400, this is the potential energy of our reactants. So our reactants have a potential energy of 400 kilojoules. Our B is from the reactants to the top of the hill, so that is our activation energy. So our activation energy is 600 minus 400, so our activation energy is 200 kilojoules. Again, activation energy is always going to be positive. The just net potential energy, if you're reading off the y-axis, those have to be positive. And so this C would be what we consider the total potential energy of the activated complex. So the PE, I'll just write AC for activated complex, equals 600 kilojoules. That value is going to be the highest of any potential energy reading, and D is going to be the potential energy of our products, which we'll call that about 150. Okay. The only really thing that's missing here is our heat of reaction. Again, that's going to be from the products up to where the reactants were. So this is our delta H, and for this problem, it's going to equal the product 150 minus reactant at, I can't write off that line anymore, minus 400 is going to give us a delta H of 250 kilojoules. Okay, we're going to look at thermochemical equations. Again, we had to look at these a little bit in the previous unit. Again, we usually do them here first, and so we'll have a little bit more information, but you've already seen these. So if we take a typical chemical equation, we got reactants, products, our phases. When we add information about the energy involved, or the heat of reaction, we simply call that a thermochemical equation. It's a chemical equation that we've added thermo information about. So it just becomes a thermochemical equation. All right? So there's two ways we can do it. Right? We can just write the chemical reaction. Afterwards, we say delta H equals negative 297 kilojoules. All right? We know since this is negative here that this is an exothermic reaction. What that also tells us is that when 1 mole of sulfur reacts with 1 mole of oxygen and produces 1 mole of SO2, 297 kilojoules of energy is released. Right? And we feel that typically as heat, may see that as light and other things. If the reaction is reversed, the sign is reversed. So if we wrote the reaction like this, with SO2 decomposing into sulfur and oxygen, that would be endothermic, as noted, and of course 297, it would have to be the same value, just the opposite sign because we reversed the reaction. Okay, and so as it says here, if we see a positive, now again, we don't always have to include the positive. We should. It's best practice to put it there, but as we know, any number that we write without a sign is assumed positive. So if we just left off the positive sign, it would still be endothermic, but it's best practice to put it there. Okay. A reversible reaction, and we've already dug into these, so we don't have to spend any time here. We know that this means it's reversible, so we could write it this way as we did first, and write it that way. We could write it this way, both perfectly acceptable ways. We just got to make sure we write the correct sign for how it's written, right? So once again, as we saw with the PE diagram, potential energy diagram, we know that any chemical reaction that is exothermic in one direction is endothermic in the reverse direction or opposite direction. Okay. We can also include the thermochemical information within the equation. And this is what we were doing in our equilibrium and Le Chatelier's principle portion. We were adding the value in here. Actually, we weren't really adding values. We often just said heat. Okay, but in reality, you would put in the amount of energy. Okay, and since we've put the energy in on the right side, it is exothermic. Okay, and so we don't put a negative sign here. It's its position on the reaction, that it's on the product side that we know it's exothermic. And here in another equation, we list it on the left-hand side or reactant side, so we know this is endothermic. Okay, so again, we could take this equation, write it this way. These two mean and say the exact same information. There is no difference on the information. It's just how somebody chooses to do it. Oftentimes when you're looking at a lot of reactions or a list of reactions, they would be set up this way, so you can just have a list of the energies involved instead of looking which side. And many times when it's just an isolated reaction or you're doing something like Le Chatelier's principle, they'll be written like this. Okay. So if we look at combustion of methane, we see the 802 kilojoules on the right hand side over here. Okay, that is telling us that this is, hopefully you guessed it, it is exothermic. And so again, what this equation tells us, that if we react 1 mole, so we go back to our basic foundation of understanding of reactions in stoichiometry, that 1 mole of methane reacts with 2 moles to produce 1 mole of CO2 and 2 moles of water. So if we reacted 2 moles of methane, how much energy could be produced? Well, since there's a 1 here implied, we know if 1 mole of methane reacts, we get 802 kilojoules. If 2 moles react, we're simply going to get 2 times 802 to give us 1604 kilojoules. We really only have 3 sig figs, so technically we've got 1.0 times 10 to the third kilojoules. Right? So we're not really going to get any more complicated than that in terms of math. Right? We can just look, if there's a 2 here, if we said if we reacted 2 moles of oxygen instead of methane, since there's a 2 here, all right, if we react 2 moles of oxygen, we're still just going to get 802 kilojoules. Okay. Now we're not going to combine this with like a stoichiometry problem and ask you to do limiting. It's just going to be something simple like this. Understanding that this means when these react at a 1 mole and 2 moles, we're going to get this amount of energy released. If we double the amount of these, we're going to get twice as much energy. If we cut them in half, we're going to get half as much. So if we took all that energy and heated 1,000 grams of water, so this is basically what you get from a natural gas stove at home. Right? If you have a gas stove, you're running this reaction, you're getting this much heat. Now if we captured all of that heat and we wanted to heat 6,000 grams of water at 20 degrees Celsius, what would be the final temperature? So if we're heating something, our equation is Q equals MCAT. So really all this question is doing is just going back and reviewing our previous questions on Q equals MCAT. We're just combining it with the chemical reaction, but it doesn't really mean that much. All we know is we have 1,600 kilojoules. So we have a Q value, we have a mass, we know it's water, so we know the specific heat. We're going to be solving for our final temperature. All right. So one way I like to do these is simply solve for delta T. Okay, instead of doing like T final minus T initial, plugging in our T initial, I think it's just easiest this way. At least for most people, it's more straightforward. So we have Q over MC. Our Q is 1,600 kilojoules. Our mass is 6,000 grams, and our specific heat of water is 4.184 joules per gram degree Celsius. We see this as kilojoules and that's joules, so we're going to have to convert that into joules. We know there are 1,000 joules in 1 kilojoule. Don't know why that line is showing up. Alright, so now we just got to plug that into our calculators and get our answer. And we get 6.37 degrees C, right? Because our joules are going to cancel here, kilojoules there, our grams there. We're going to be left with per degree C. And so we have a 6.37 degree change. All right, since our initial temperature only went to 1 decimal point, we can stick with using 6.4 degrees C, because that's all we're going to be really allowed to use or able to use in our calculation. So what would be the final temperature? So we could like write it out mathematically, but we know we're heating this, so the temperature had to go up by 6.4. So when we add that to 20, we're going to get a final temperature of 26.4 degrees C is our T final. So that is the end of our thermo unit and the end of our new material for our school year. It's been interesting the past few weeks, past couple months, I guess. I hope you found some of the stuff interesting and hopefully learned a little bit, and hope there's some that you can take with you when you leave chemistry. So we will see you hopefully at some point, so you can come by, visit next year, and that is all.
Have you seen Junior's grades?